The second part of the lesson for section 21.4 is going to use what we learned about composition of functions and discuss how we can use that information to find inverse functions. And remember that inverse functions are very helpful when trying to solve equations.
This next example, we have the function f of x is 2x and g of x is 1/2 x. So I want you to pause the video here, try this example, and then resume it to check your answer. So for this example, you should have found that f of g of x gives you x, and that g of f of x also gives you x. In this case, they are the same. So it does happen, and we'll talk about why here in a second. Let's look at one more example here, example 26, and we've got the exponential function and the natural logarithm function. You should remember these from Tech Math 3. The exponential function is the number approximated by 2.718, this function e, and raised to a variable exponent, and the natural log of x is its opposite or its inverse. So let's look at f of g of x. If we take f of the natural log of x, we end up with e to the natural log of x. And again, if you remember from Tech Math 3, you have e to the natural log of x. This will give you x. And if you have g of f of x, you would have g of e to the x, which is the natural log of e to the x, which again gives you x. And if you need some review of this, please check out the video listed under the course outline for this section. There is a link to review exponential functions and natural log functions if you've forgotten from Tech Math 3. But this leads us to what we know as the inverse function. The inverse function in math, this is essentially a function, and we're going to put this in quotes because it's not always a function, that reverses another function. You can kind of think about these as being opposite functions, and again I had to kind of put that in quotes because there are times when the inverse function is not actually a function and we have to restrict its domain so that it can be considered a function. Another definition that we can use for this is that if we have two functions, f of x and g of x, such that f of g of x equals x, as does g of f of x. So we always have to get back to x for this definition. And the notation that we use for this is f with a -1 exponent on x. Now this notation can be a little confusing for some students. This exponent is not an exponent, it's an inverse symbol. When this -1 is raised up here on a function, it's considered to be an inverse. When it's on a variable or a number, it is considered an exponent, and that's when we deal with reciprocal. But inverse and reciprocal are not the same thing. Again, -1 on a function is inverse, -1 on x or a number is a reciprocal, not the same thing. To find an inverse polynomial function. This process is pretty straightforward. We're just going to first start off with switching the x and the y variables. We're going to exchange those two, and then we're going to solve the resulting equation for y. So we'll start off with something simple, a linear function, which means our inverse should also be a linear function. So we're going to switch x and y here. So we're going to start off with x equals 2y minus 7. So again, all I did here was instead of y I wrote x, instead of x I wrote y. Now we just look at this new equation and we solve for y. So order of operations, we're going to add 7 to both sides. So we get x plus 7 equals 2y, and then we divide by 2. So we end up with our inverse function being x plus 7 over 2. And we can check to make sure this works by composing these functions. So f inverse of f of x. So if we plug f of x in to our function that we found, we have 2x minus 7 plus 7 over 2. Well, 7 minus 7 is 0, so we're left with 2x over 2, and that just gives us x, which again is what we're looking for. We want the inverse of the function to be x. We can check it the other way as well by plugging the inverse into the original function and making sure that we get x as well. You should. The other thing we want to talk about is what is the domain of this new function. So you look at this function, you say, okay, this is a polynomial, so it should be all reals. But the other thing that we have to be careful of here is that the domain of the inverse is the range of the original function. So again, this original function was a domain of all reals and a range of all reals. No matter what you plug in, you're going to get some number on the number line from negative infinity to infinity. And so in this case, our domain is just negative infinity to infinity. Again, all real numbers. I want you to pause the video here and try the next example. The only difference here now is that we have a squared, so we're going to have to do that square root at the end, but the process is going to still be the same, not too difficult. So pause the video here, try it out yourself, and then resume the video to check your answer. So for this one here, we should have ended up with the square root of x plus 9 over 5. Again, that whole fraction is under the radical there. Again, we can check our work. In this case, I'm going to plug f of inverse into f. Again, you can do this either way, and you do want to do this both ways to make sure that it works. It's a little easier, though, to see this one. So we would have 5 times the square root of x plus 9 over 5, quantity squared, and then minus 9. So if you square that whole thing, it gets rid of the square root, so you just have 5 times x plus 9 over 5, minus 9. 5 divided by 5 is 1. So you're left with x plus 9 minus 9, which is indeed x. Like I said, you can do it the other way. You would see the same thing if you plug that in. It's actually not too bad. You just end up with the square root of x squared, which ends up being x. So the domain for this one is going to be, again, we need to make sure that this domain here, x plus 9 over 5, has to be greater than or equal to 0. Multiply the 5 over, and you end up with x plus 9 has to be greater than or equal to 0 still. And then again, you subtract that 9 over, so you have that x has to be greater than or equal to negative 9. And like I said before, if we were to graph this original parabola, the range of the original function would have been negative 9 and higher. So we would have been down here at negative 9, and we would have had a parabola that goes up like this. So our range here goes to negative 9, which, again, the range of the original function is the domain of the inverse. So in this case, this works out the domain of the inverse is x is greater than or equal to 9. We can write this in interval notation, which would be that we are starting at negative 9. Again, we've got that bracket there because it's greater than or equal to, and we're going up to infinity. Let's look at another example here. This one's a little bit more involved. Just because it's got an extra term in here, that 5x is going to kind of throw things off. So if we rearrange this, we have exchange what we need to. We have x is equal to 2y squared plus 5y minus 3. Like I said, again here, just kind of moving things around and taking the square root isn't going to work because we still have that 5y there. In this case, we're actually going to want to go back to the quadratic formula, and we want to set this equal to 0 in order to use that properly. So we're going to end up with 2y squared plus 5y minus 3 minus x equals 0. And in this case, our a is 2,
our b is 5, and minus 3 minus x is c. So if we go over here to the quadratic formula, we have that y is equal to, this time, because that's our variable that we're concerned with, b, so negative 5 plus or minus the square root of 5 squared minus 4, a is 2, and c is this lovely negative 3 minus x. All divided by 2, in this case, a is 2. We simplify here a little bit. Y is equal to negative 5 plus or minus the square root. We've got 25 minus 4 times 2 is 8 times 3 is 24, positive 24. So we got both those negatives. And then 8x. All divided by 4. Do one more simplification here. We can add that 24 and 25, so we end up with negative 5. We're only going to deal with the positive here. Again, with functions, we want to make sure that we have only one output. So it would be the square root of 49 plus 8x all over 4. Again, we can check to make sure this works. I don't quite have the room here, but you can check that yourself to make sure that f of f inverse gives you x, and vice versa. As well, the domain here, again, if we look at this, we've got a parabola. So if we were to graph this thing and again use our minimum function, we see that the lowest point here, y value, is negative 6.125. So that is going to be our domain for this function. So our domain here, and I'll write it up here at the top. Again, this is the domain of the inverse, is going to be, again, starting at negative 6.125 and going up to infinity. Again, we can see that based on the graph. We can also look here, if you just look at the radical, again, that's going to be what would cause us problems as far as real numbers go. And so, again, if we wanted to look at this, 49 plus 8x would have to be greater than or equal to 0. Move the 49 over, you get 8x has to be greater than or equal to negative 49. And then again, dividing by 8 here, we get that x would have to be greater than or equal to negative 49/8, which is the negative 6.125 that we found. So again, the domain of our inverse function needs to be the range of our original function f. And so this works out here. We have one last example here, and this one is a rational function. You can see that we're going to have an issue here with the domain of the original function where that denominator is 0. I have the graph here. You can see again the range looks like it hits just about everything, but there is this horizontal asymptote here. And if you recall from our lesson on horizontal asymptotes, you notice that since these are the same degree, x minus 3 and x plus 5 have the same degree, 1, that you can just divide the coefficients and we get that horizontal asymptote to be 1. So the graph here is never going to touch 1. Our range is never going to touch 1. It's going to go everywhere except that. We know that the range of the original function, x minus 3 over x plus 5, is never going to touch 1. So it's going to be that open interval there at 1. That means the domain of the inverse is also going to leave that point out. So let's go through and solve the problem though to find the inverse. Again, switch, we've got x is equal to y minus 3 over y plus 5. This one is just some simple algebra. We're going to multiply the y plus 5 over to the other side. So we have x times y plus 5 equals y minus 3. And now this is, you're kind of wondering, how do we get those y's to get together? Well, we're just going to distribute the x. So we have xy plus 5x is equal to y minus 3. And then you need to put the y's together. So we'll move them to one side. We'll have xy minus y equals, we'll move the 5x over, minus 5x minus 3. And then we'll factor that y out on this side. We have x minus 1. Don't forget the 1 because there is 1 there. And negative 5x minus 3. Divide that over, so y is equal to, and again this is our inverse function, is negative 5x minus 3 over x minus 1. This makes sense. We know here our denominator here can't be 1. And so that makes sense for our domain that we talked about before. It worked out. So this is just a basic overview of how to find inverses as well as their domains. Do some more practice examples to reinforce your knowledge for this concept.